Our next speaker is Hoi Yip from Hong Kong, who will talk about additive properties of multiplicatively defined sets. Please.
Okay, yeah, thank you very much for the attention. Sorry for the introduction. So I will talk about additive properties of a multiplicative defined set. This is a joint work with Ernie Coote, who was my postdoc mentor at Georgia Tech, and his PhD student Ginger Mao. In this talk, we will focus on this question, namely, if we have a multiplicatively defined set in positive integers, can we say something about its additive property? By multiplicatively defined set, I mean there are many such examples. For example, we can ask, can we say something about the additive properties of primes? Uh, can we say something about perfect squares, perfect powers, or wide smooth numbers? So I think for most of this kind of multiplicative defined set, this question is far from being understood. Um, so let me just like briefly say something about the sum product phenomenon because this is related to the main question in this talk. So for the sum product phenomenon, basically the setting is that we have some nice ring R and we have some large finite subset A of this ring R. Then we are saying that the set A cannot be both uh, very additively and also very multiplicatively structured. So by that, I meant that if we consider the sum set A plus A and also the product set A times A, then one of them should be much larger than the size of A. Unless we are in the special case where A has some algebraic structure, namely A is close to be a subring of the ring R. Because in that case, like A plus A and A times A are essentially just A itself. So the sum product phenomenon just says that unless we are in a subring setting, then one of the sum set or the product set has to be much larger compared to the size of A. So in particular, if we are working in the integer ring, then we know there is no non-trivial subring, so we know that we always have either the sum set or the product set have to be much larger than the size of A. So in particular, we have the famous sum product phenomenon as a sum product conjecture made by Aldrich and Samrady. So they conjecture that like either A plus A or A times A have to be roughly quadratic in the size of A. So I should mention that there was some recent breakthrough on the sum product conjecture over real numbers. In the real number setting, the conjecture has been disproved, inspired by the disproof of the unidistant conjecture of Aldrich. But I guess for the integer setting, it seems people still believe that the sum product conjecture should be true. But anyway, so in our talk, we will only focus on the integer setting. Okay, so because of this sum product phenomenon, if we have a multiplicatively defined set, then we shouldn't expect that it still have rich additive property because otherwise this would violate the sum product phenomenon. So basically, we should expect that for multiplicatively defined set, the additive property shouldn't be too strong, right? So one thing we would like to do is to make this statement more precise. So I guess we can try to ask a few more specific questions. So here are some more specific questions that we can ask. And these are also some questions that we will try to study in the next few slides. So first, one natural question we can ask is, can we say something about the arithmetic progressions contained in the set S? So for example, we can ask what's the longest arithmetic progression containing S? So this is one natural question to ask. And then we can ask, can we say something about some set containing S? So more precisely, if we have like a non-trivial sum set A plus B containing S, can we say something about the upper bound, the minimum of the size of A and size of B? So this is also a very natural question to ask. And then we can also ask, what's the maximum dimension of Hilbert cube containing S? So I will define Hilbert cubed in the next slide. And another question we want to partially address in this talk is we want to see if there is a connection between these three questions. So whether there is a connection between arithmetic progression, sum set, and Hilbert cubes. Okay, so in this slide, I will define Hilbert cubes in case some of you may not know its precise definition. So to do that, let me first introduce the definition of subset sums. So if we have a set A, then the set of subset sum is basically just we take a subset B of A, and then we consider the sums of the element of the set B, and then we consider all possible subset B, and then this forms a set. So this is uh, known as the set of subset sums, and we use sigma A to denote that. So sometimes we would like to work on multi-set instead of a set. For multi-set, we can still define the subset sums. So there we can try to view A as a sequence, and then basically we just take a subsequence and we take the sum, and then we consider all possible such sums. So for a multi-set, we can still define sigma A. And then for Hilbert cubes, basically just a translation of the set of subset sums. Formally, we can try to have A0, A1 up to AD. The Hilbert cube edge A0, A1 up to AD is just A0 plus 0 A1 plus 0 A2 up to 0 AD. So basically, this is just A0 plus the subset sum of the multi-set A1 up to AD. Okay, and then we would like to kind of measure the size of a Hilbert cube. So one thing we can do is that we can measure the dimension. So the dimension D here is just how many elements are there in the corresponding multi-set. Okay, so this is a Hilbert cube, the definition of Hilbert cube. So we can kind of think about the maximum dimension of Hilbert cube containing a multiplicative set S as a kind of a measurement of the additive complexity of the set S. Uh, so uh, studying Hilbert cubes in a multiplicatively defined set is kind of interesting. Okay, so next maybe let me just introduce some kind of questions that have been studied uh, related to like studying the additive properties of a multiplicative defined set. So one of my favorite questions is this question by independently asked by Aldrich and Moser, which asks, can we say something about some set containing squares? So basically, we have a set A, a set of positive integers A, and we know that the sum of every two distinct element in the set is a perfect square. And then we would like to see how large can this set A be. So this was asked by Aldrich and Moses in 60s. And I think the best known construction is due to Lagrange and Nicholas independently, where they found a set of size 6. And I think this is the best known progress. So basically, that means that we don't know if there is a set of size 7 which satisfies this property, namely the pairwise sum are always squares. And on the other hand, if we assume the uniformity conjecture, very deep conjecture in arithmetic geometry, then we know that the answer should be no, because we can try to associate this question with like a hyperelliptic curve, and then can try to bound the size of the set by the number of rational point on that curve. So probably the answer is no. And yeah, and also because the set of perfect squares is multiply defined, we should also kind of expect the size to be small by the sum product phenomenon. Okay, so the best known progress is basically saying that if we only consider a set A containing 1 up to n such that a pairwise sum is a perfect square, then we can show that its a set cannot be too large. So basically, it's bounded by a constant time log n. So this can be proved by studying the finite field models of this question. So basically, we consider the setting of FP where some set is containing a set of squares. So from there, we can get some estimate, and then we use like shift method to say something about integer version. Um, so this is essentially the best known upper bound. And then if we assume like for example the Paley graph conjecture about character sums over finite fields, then we can refine the bound from the finite field model, and then if we still apply the shift method, we can probably get something like log n to the power little one. But this is uh, like very far from maybe the implication of the uniformity conjecture, which says that the size of A should be absolutely bounded. Okay, so that's like the subset containing perfect squares. And also we know that actually Euler already proved that if we have a arithmetic progression containing the perfect squares, then the length has to be almost 3. So kind of studying arithmetic progressions in perfect squares is easy. Studying some set in perfect squares seems to be very hard. So maybe we can answer a different question like can we say something about Hilbert cubes containing perfect squares? There are a couple of papers studying this question. So I think the best known result was due to Dittmann and Elsels in 2015, where they showed that if we assume that this kind of AIs are at most n, then if this Hilbert cube is containing the set of perfect squares, then the dimension should be at most log n. So you can see that here, like the answer is still not satisfactory because, I mean, we should conjecture that even if we have a sum set in perfect squares, the size should be already absolutely bounded. So in terms of Hilbert cubes, of course, it should be also absolutely bounded in terms of the dimension. But at least you can see that here the bound is log n, which is much better compared to the log n bound for the subset. So this might suggest that studying Hilbert cubes is easier compared to subset. And intuitively, this is easy to understand because Hilbert cubes are much more rigid compared to subset because for Hilbert cubes we need to have yeah, things like this. So it has to have a very strong additive structure so that we can contain a large Hilbert cube. Um, so kind of our main result is kind of saying that this is indeed true in certain sense. Okay. But before that, I just want to formalize the question that we want to study. So basically, we have a subset of positive integers, say R, and this set R often has some nice arithmetic structure. Usually has some nice multiplicative property. Then the question we want to kind of study is what's the maximum possible dimension of Hilbert cube containing R? Uh, so more precisely, that means what's the largest integer d such that we can find some non-negative integer a0 and some positive integers a1 up to ad, such that this Hilbert cube h a0 a1 up to ad is a subset of R. Okay. So usually this kind of R, I mean, we want to study some kind of asymptotic results. So usually we take some S, which is an infinite set of arithmetic integers. For example, in the previous setting, we just take S to be the set of perfect squares. And then we do some truncation. For example, we only consider perfect squares up to n. Then we call this to be R. And then for this question, we have some answer depending on n. So now we can try to study the asymptotic of this largest dimension, which is a function of n. So we would like to kind of study how this maximum dimension d grow asymptotically with n. So this is the main question in this kind of study. So this question has been studied for various arithmetic set by many people. So for example, by Aldous Sarkozy Stewart, by Guy Marty, by Dima Elsos, and many people. Okay, so before mentioning the main result, I just want to mention some connections between this question and sum set and arithmetic progressions. Um, the kind of easy observation is that arithmetic progressions are actually Hilbert cubes. Basically, if we have a arithmetic progression, say like a0 plus q, a0 plus 2q up to a0 plus lq, this can be viewed as a Hilbert cube because we can just take our like multiset A to be the multiset with one element Q with multiplicity L. So our multiset A is just like L copies of the same element Q. And then if we study the subset sum of this, we just get like Q to Q up to LQ. So if we just consider A0 plus this, then we just get this arithmetic progression. And this is, of course, just a Hilbert cube of dimension L. So basically, this means that a lower bound on the dimension of Hilbert cube containing our set of integers R is basically the longest arithmetic progression containing R. So that's kind of a nice connection between arithmetic progressions and Hilbert cubes. So we use the notation Gn to denote the largest length of progression containing S intercept with the first integers. Somehow we believe that this kind of arithmetic progression constructions should be roughly optimal because if we have a multiplicatively defined set S, then you shouldn't have a rich additive structure. So the arithmetic progression construction, I mean, should be the best Hilbert cubes containing S. So this is kind of a heuristic. Of course, we cannot make this very precise, but we can maybe prove something like once we also have some control on some set containing S. So that's the next thing I want to mention. As I discussed earlier, if we just have a general set S, then just using arithmetic progressions is not enough to estimate the dimension of Hilbert cubes, because S might still have some additive structure. For example, S might have some non-trivial subset structure. So just using arithmetic progression is not good enough. So because of that, we would like to also introduce a quantity which measures like some set containing the set S. We would like to consider, for example, K for some set. So we have this K set B1 up to BK. And then suppose that we have, for example, this all of them, the sum is containing S, and they are also subset of N. Then we can try to measure what's the smallest size of this subset, and we use Fkn to denote that. It turned out that there is also a nice connection between dimension of Hilbert cube and this function Fkn. Because roughly speaking, you can try to decompose a large Hilbert cube into into the sum of smaller Hilbert cubes. Uh, because, for example, let's go back to this slide. So here we have, like, you can see that this is essentially a sum of this set, right? So you can divide this set into k part, and then you can see that this becomes the sum of k set. So we can try to like upper bound on the dimension of Hilbert cube containing S intersect n by constant time Fkn. Just a quick summary, we discussed that the dimension of a Hilbert cube is lower bounded by the long list progression, the length of the long list progression, and on the other hand, it's upper bounded by this sum set function Fkn. So we have some lower bound and we have some upper bound, but probably it should be close to the lower bound as we discussed earlier. Basically our framework says that under certain assumption, this is roughly true. Right. So again, Gn is just a long list progression containing S intersect n, and this Fkn corresponding to the minimum set Bi, a minimum size of the set Bi, such that this kind of Bi a subset of n, and the sum of these Bi's are containing S. So we have this function Fkn and Gn. That just assume that this Fkn go to infinity as n go to infinity. Then what we can show is that if we have a Hilbert cube containing S intersect n, then the dimension can be controlled by Fkn and Gn. More precisely, it's bounded by the maximum of Fkn to the epsilon and Gn. Where this epsilon is arbitrary small constant, and here the implied constant depend on both k and epsilon. You can see that this should be sharp in certain cases up to the implied constant. The reason is that we already know that the size of the largest Hilbert cube should be lower bounded by the size of the progression. So let's assume that this Fkn epsilon is smaller than Gn. Then this bound just roughly says that the size of A is upper bounded by Gn, and Gn is a lower bound on A, on the size of maximum Hilbert cube. So if we are in the nice setting that Fkn to the epsilon is bounded by Gn, then we know that the size of the dimension of the largest Hilbert cube containing S intersect n is just roughly Gn up to the implied constant. It turned out that if we just take a random set S with probability half, then we can indeed show that this Fn is bounded by a polynomial in Gn. So unless in that setting, actually, almost surely, like the Dong-List progression is the largest dimension of the Hilbert cube containing S. And also, if we are in the setting of a multiplicatively defined set S, because it has no obvious additive structure, so we should kind of expect that this Fkn can be bounded in terms of polynomial in Gn. This result should potentially give a sharp bound uh, up to the implied constant. I guess I can skip this slide maybe. And then in the last 2 minutes, I would just want to mention a very quick application about Hilbert cubes containing smooth numbers. So this was kind of first studied by Eldridge, Sarkozy, and Stewart in 1994, where they just studied what's the largest dimension of Hilbert cube containing certain smooth numbers. So in our case, that's shown that we study Hilbert cubes containing log n to the alpha smooth numbers, where alpha is from 0 to 1. And here we also shown that all the AIs are m mod n. So we can show that in this case, the largest dimension of Hilbert cube is a constant time log n to the power alpha. I want to first mention that this bound is optimal up to the implied constant because you can just use a very simple construction. So you can pick this A0 to be 0, and then you can pick this A to be the multiset consisting of element 1 with multiplicity log n to the alpha. Then, of course, this Hilbert cube is just basically the interval from 1 to log n to the alpha. So, of course, everything is log n to the alpha smooth. So this shows that this bound is essentially best possible up to the implied constant. And to prove this result is also not difficult because we can try to estimate what's the longest progression in this log n to the alpha smooth numbers. So that's roughly just log n to the alpha. It's a result of Surrey and Tiedemann in 1990. And for the regarding the sum set, we use the result of Ruja to show that it's bounded by log n to some power depending on alpha. And then because you can see that this Fn and Gn are comparable, then by our main result, we just know that it's roughly just bounded by a constant times Gn. Right. Yeah. So that's everything I want to talk about. Thank you for your attention.
All right. Thank you very much for a very nice talk. Are there any questions for our speaker? If not, well, thank you again.
Thank you.
And our next talk will be in 3 minutes. So Akshat, if you can upload your slides.
Yep. Let's see. Share. Yeah.
Looks
Are
pretty
people
good.
able to see this?
Yes, you might make it bigger if you can. That's
Yep.
excellent. Okay. We'll wait. We'll wait 2 minutes.
Okay, that's fine.
So we're close to the schedule, and
I think this works. I think now we're in full screen.
looks great.
Perfect. Wait, oh, don't go on slideshow. Full screen. So it's 20 minutes talk plus 5 minutes for
25.
question.
No,
Okay.
25.
Okay.
And um, and there's always a minute or two left for questions. But somehow it's a miracle, but we have 80 speakers in this conference, and we've stuck to the schedule so far. So far. This is
Okay,
the
I
last
will.
day. I'm counting on you not to mess it up.
Okay, I will do my best not to derail the conference
Thank you.
completely.
Thank you. It is kind of a miracle. I don't quite understand how it's worked so well so far, but it's nice.
Yeah, and it's really nice. You've got like speakers from so many different countries and places.
Yeah, no, it's